So when we're thinking about the truth tables, the truth values that is, for a conditional statement, it can help to recall the way that we defined the pieces of a conditional statement back when we introduced it. That we called the two parts of a conditional, if P then Q, the antecedent and the subsequent, respectively. Where what this means is that P gives a necessary condition for Q to exist. If Q exists, then P has to have existed. And that informs some important parts here for the truth table we're going to get, as the way that this ends up working out is if we have that both P and Q are true, then the conditional P implies Q, if P then Q, is also true, and that one should make a fair amount of sense. If P is true and Q is false, then the conditional is false, and I'll explain why that happens there in a little bit. But first I want to get to the two odder cases, where if P is false, then regardless of what happens to Q, whether Q is true or Q is false, the entire conditional is true. And that's not intuitive. But the reason why it happens is because what happens with P is considered necessary in some sense for what should happen with Q. And if P doesn't happen, then technically speaking, nothing else really matters for our conditional statement. Anything else we might be interested in, anything else we might want to know, who cares? The condition is broken, so the conditioning is non-substantial. And as a result, we say that the conditional statement, if P then Q, is trivially true if P is false. So we just get that those cases are true because, well, nothing we care about can possibly happen anyway. The one case that really matters is what happens when P is true and Q is false. Because there, what we're saying is the condition that is supposed to give us Q, that is P, fails to give us Q. It doesn't give us what we're supposed to get there. And so that means our conditional statement, the compound statement built explicitly around that conditional relationship, doesn't work. Hi everyone, quick cut in here about this because I feel like I didn't give quite enough justice to why the conditional statement thing works the way it does. So before we get to our example, before we get into our other part there, I have something a little bit lighter to help introduce why this truth table happens to work. Where we're going to think about a classic joke. And we're going to have the statements P is the chicken crossed the road, and Q is the statement it got to the other side. So if we have the conditional if P then Q, then we have if the chicken crossed the road, then it got to the other side. So if P is true, if the chicken crossed the road, and Q is true, then the chicken got to the other side, our whole statement is very obviously true. That's our first case for the conditional there. It's the cleanest one. It's the one that we kind of want to get when we set something like that up. Then for the second case, if we have that P is true, that is, the chicken crosses the road, and we have that Q is false, the chicken does not get to the other side, then the statement, if the chicken crossed the road, then it got to the other side, doesn't really make any sense, because the thing that was supposed to allow the chicken to get to the other side didn't. The condition we have doesn't work, so we say that the conditional in that case is appropriately going to be false. And then finally, for our cases where the chicken does not cross the road, that is, where P is false, our conditional, if it crosses, then it gets to the other side, is no longer really relevant. It doesn't really have any meaning because the thing that we're supposed to be building around never happens. And in those cases, we trivially say that the conditional is true because it technically can't be false. It's a little arbitrary in there, but that's how that one works. Anyway, let's get back to the video proper so we can finish talking about this and get to a more symbolic example. So that's our only case where conditional happens to be false. If the first part is true and the second part isn't. In any other case, we say it is true. So let's get an example here with a bit more exacting parts in terms of a truth table for how these get built working with conditionals. So for this, we want to build the truth table for if not Q, then not P. Where we can start here very basically with the two main parts we have for this sort of argument, that is our two simple statements, P and Q. So the four parts, true, true, false, false, true, false, true, false. Then we make the negation of each, where we just flip the truth values of Q and P. In this case, I'm going to write Q first, not because it has any great meaning, but usually when we do these things, it's kind of nice to have the columns organized in the same way as our final answer is going to be, as our main statement is going to be. And then at the very end, we can finish this off by writing in that conditional, where we have that the cases we look for are when not Q is true and not P is false. Because in the first case, when both are false, the conditional is trivially true. Then in the second case, we have that not Q is true because Q is false, and not P is false because P is true, which is weird and kind of circular, but it gets us to that conditional being false. That's, again, our most important of the scenarios. And then for the last two, because Q is false in the first case, doesn't matter what happens, or not Q, excuse me, is false in the first case, doesn't matter what happens to not P, whole thing gets to be true for free. And then in the last case, we have that they're both true, and that's our best case scenario, really, when dealing with conditional statements. So this is, roughly speaking, how conditionals work, at least in terms of truth value. Let's next talk about how biconditionals work in this same sort of construction.